Yeah, thank you very much for the chance to speak here. So I'm going to talk about mostly causal duality with some aspects of the role that curvature can play, and then about some results about Calabi structures and how they behave with respect to causal duality. So this is work in part with Andrey Lazarev and in part with Manuel Rivera. And let me just start because causal duality means many different things to many different people with what kind of causal duality I'm going to talk about. And so I'm going to start with a very classical associative causal duality between the exterior algebra and the symmetric algebra, um, which is sort of this correspondence, which is encapsulated, for example, by saying the endomorphisms over the symmetric algebra of the trivial module is exactly the exterior algebra. And almost conversely, the endomorphisms of the trivial over the exterior algebra is somehow completion of the symmetric algebra. And so this very classical correspondence has an incarnation in modules. And so one can sort of essentially tensor together the symmetric algebra and the exterior algebra and put a pseudo differential on that. And then take this causal complex and tensor modules to go back and forth, right? So I can take some module of the exterior algebra here, maybe in color, and then I can tensor that with this causal complex over my exterior algebra. And then I have left over the symmetric action. This gives me a module over the symmetric algebra. And I can, go back and forth. And then if I restrict myself to the bounded derived categories of graded modules, I get this correspondence, this equivalence of categories, of derived categories. And one interesting thing this does is that if I start with a trivial module for the exterior algebra, it goes to the free module for the symmetric algebra, and vice versa. If I take the free rank 1 module for the exterior algebra, it's identified with the trivial module of the symmetric algebra. This is a very beautiful correspondence, and of course, it's not just true for the symmetric exterior algebra, but more generally for causal algebras, which is sort of quadratic algebras, augmented quadratic algebras with a certain homological structure that I'm not going to talk about because I'm going to be interested in generalizing this. And by the way, if there's any questions, or if I go too fast, you should feel free to interrupt as I speak. Right. So, and when one looks into generalizing this, one thing to do is to notice this restriction to the graded modules here, right? So graded modules means we put sort of V in an extra degree 1 and an Adams degree 1 and only look at graded things. And the reason for that is very explicit, because if I don't do that, then on the right-hand side, I look at modules of the symmetric algebra, so modules of the polynomial algebra. There's a lot of one-dimensional modules corresponding to different points of the associated affine space. Right, and so I can look at all these different trivial, not trivial, but these different one-dimensional modules corresponding to like skyscraper sheets on the right, if you want to think about it geometrically. And if I take any of these and I look at them on the other side, they disappear in the derived category. So I have to exclude them, and I exclude them by saying I only look at graded modules. So X can't act as some scalar, X has to act as 0. Okay, but of course, this is a bit restrictive, right? The full derived category of the symmetric algebra is also interesting, and one can refine this correspondence. And this correspondence is refined. So this is following work of Lefebvre Hasegawa in his thesis more than 20 years ago, where he observed already that the exterior, if we look at what is the exterior algebra, and not just the derived category, but some refinement called the co-derived category, then it's equivalent to the full derived category of the symmetric algebra. So there's sort of some different way of looking at a derived category here, where we don't identify all quasi-isomorphic objects, where we don't quotient all the acyclics, where in particular the image of things like could have things like kx over x minus lambda here as this one-dimensional module, and that would go to something which is acyclic, but which is not 0 in this co-derived category. Let me tell you a little bit about these exotic derived categories, of which the co-derived category is an example, the example that I'm going to talk about some today. Right, so we can always look at the derived category by identifying complex up to quasi-isomorphisms. And then there's a whole host of exotic derived categories that go back to work of Becker and Positzelski, also studied by Krause, by Jorgensen. So different things coming together. Positzelski really sort of has the most complete treatment, and this sort of co-derived, contra-derived, absolute derived, completely generated of the second kind. Also incoherent sheaves, if you've come across this in a geometric setting, are also an example of an exotic derived category, or an enrichment or enhancement of exotic derived categories. And so this just means we don't invert all quasi-isomorphisms, but so these live between the derived category and the homotopy category. So we do invert all homotopy equivalences, and then we invert some extra maps, but not all quasi-isomorphisms. And so, for example, the co-derived category, we kill all the objects that are co-acyclic, and this just means we start with short exact sequences, and say if I have a totalization of a short exact sequence, that's going to be zero. That's sort of acyclic in a very strong sense. And then I sort of take these totalization of short exact sequences, I close under summand, and I close under arbitrary direct sums. And this is the subcategory of coacyclics. I quotient those out, I get the co-derived category. The details are not so important now. It's just sort of saying there is this refinement. And I'm going to give an example of how this refinement can tell us more things than the usual derived category that comes from topology. So if I look at the cochain algebra for topological space, it's just singular cochain in the topological space, I could look at the derived category and say that's a DG algebra, that has a derived category. I could look at modules over this DG algebra. And if I unravel this topologically, this is equivalent to a category of sheaves on X. And these are sheaves, complexes of sheaves, whose cohomology is just copies of the trivial sheaf. So I have my trivial sheaf on topological space. I can extend that in various ways to build this derived category. So it tells me something about the variety, about the manifold, it tells me about the cohomology, but it doesn't see, for example, anything about the fundamental group. Because the fundamental group would be reflected in non-trivial local systems, for example. And the co-derived category, I have to add this word here, which I'm going to explain in a second. The co-derived category is actually equivalent to the category of all complexes of sheaves on X whose cohomology sheaves are local systems. Right, so this is now much broader, right? The cohomology sheaves are not just restricted to be the trivial or copies of the trivial sheaf, but they could be arbitrary local systems, arbitrary representations of the fundamental group. So somehow refining our notion of a derived category gives us this much larger category that reflects much more information, in this case about the manifold X and in general about the DG algebra, of which we take this. Okay, so with this in mind, let's go back to our little example, and let's talk about what curvature has to do with any of this. So if I have a DG, so I take the DG algebra here. This is just, again, I'm writing out the exterior algebra on one generator. I'm just going to writing out because I want to modify the definition a little bit in a second. And then I can compute the Koszul dual, and which is the self-x of the trivial module. I have a trivial module. I can compute self-x, right? So this looks like endomorphisms or derived endomorphisms over A of K with K. Oh yeah, here I already wrote it down. Here it is. And one way of computing this is to resolve K with the bar construction, with the bar resolution. And if I resolve K with the bar resolution to compute this, I get something which looks like this, right? So I have A, I reduce it, I quotient out a copy of K, I shift it, I take some free algebra on that, which I complete. I put a suitable differential, which comes from the multiplication rule and from the internal differential, which in this case is 0. And I can compute that this is somehow a power series algebra. So this is sort of a basic computation. And it's of course, earlier we were saying we have this Koszul duality between the dual numbers and the polynomial algebra, which means the exterior algebra on V and the symmetric algebra. So it's dual and polynomial algebra. And here the dual is a little bit different. We have this completion. And I'm going to explain to you why this appears. But for now, let's just take it in stride. And let's modify things. And let's say, what if I change my my dual numbers by instead having that the squared of epsilon is lambda, where lambda is just some non-zero scalar. I've been a little bit sloppy between C and K. It doesn't really matter what field we're working over, some field. And if I do this, so first of all, I have to use Z2 grading now for this to make sense, right? Because I put epsilon in degree -1, so epsilon squared to be a scalar, I have to be Z2 graded rather than Z graded, but that's allowed. And now what happens is I no longer have a trivial module, right? I don't have an action. I don't have a trivial module over this. I don't have an augmentation of the algebra because of this new rule. And right, because epsilon has to go to 0 for degree reasons if I map to k, but then epsilon squared can't go to lambda. So this doesn't have an augmentation. And now the insight is it doesn't matter. So this thing doesn't make sense anymore. I don't have self-x of the identity, of the trivial module. There's no trivial module, but this thing still makes sense. I can write this down. I have to do something to get this reduction here. So I have to choose splitting of my map K to A, and then I write down a bar construction like so, which again has, the same thing happens on the underlying set. It's this tensor algebra on the reduced algebra shifted. I have a differential induced by the multiplication of the internal differential, which in our case would just be 0. But then in general, the differential need no longer square to 0. The reason the differential squares to 0 in the bar construction is exactly because this decomposition of A into A bar plus K is compatible with differential multiplication. If it's not compatible, I can carry around this incompatibility, but in my computations, it gives me a curvature term. Curvature means that I have a differential, which isn't actually a differential, it's a pre-differential, and dA, sorry, this should be d squared A, is no longer 0, but is actually the commutator with some element h in degree 2. This is what a curved algebra is. And the claim is that if I try to take the Koszul dual of this very basic, right, it's a two-dimensional algebra, it's sort of the first deformation I can do of the dual numbers, I am led naturally to look at a curved algebra here. And in this case, my curvature term is exactly lambda, which was exactly my deformation here. And right, so in this case, the differential is 0. So d squared of A is 0. Well, indeed, d squared of A should be the commutator with h, but we're in a commutative algebra, so this commutator is 0. Nevertheless, I should look at this as a curved algebra, because if I look at it as a curved algebra, I can do this for arbitrary DG algebras, which are not necessarily augmented. And so this is the sort of basic appearance of curvature. This is actually a special case of, well, so let me first say this. So this fits into Koszul duality, as I was stating it earlier, and the derived category of A is the co-derived category of the bar construction of A. And here this bar construction is this bar construction, which is curved. And because this is curved, I couldn't even use the derived category if I wanted to, even if I didn't know it was wrong, even if I didn't know it doesn't give me the correct correspondence. This isn't even defined if BA is curved, because the derived category needs quasi-isomorphisms. Quasi-isomorphisms needs homology. Homology needs d squared equals 0. D squared equals 0 is no longer guaranteed. So there is no derived category, but there's always a co-derived category, because I can still talk about exact sequences, I can still totalize them, I can still take their arbitrary sums. And so this Koszul correspondence now, if I plug in my example here, I get sort of a classical result back, which is the Koszul duality between Clifford algebras and matrix factorizations for non-degenerate quadratic form. Right, so my lambda e squared was an example of a non-degenerate quadratic form, and so this deformation of the exterior algebra becomes the Clifford algebra, and I could look at modulus of the Clifford algebra, and modulus of the Clifford algebra is exactly the same as the category of matrix factorizations for this, where the potential is given by this quadratic form Q. And there's a classic result of Buchwald-Eisenberg, Eisenbart and Herzog. And it's an example of sort of a curved causal duality. So many factorizations can be defined in many different ways, but one way to define them is as modules over a certain curved algebra, which is sort of a, in this case, because we're completed a power series algebra here, a zero differential and a curvature term Q. And then the modules over that, in a way that is exactly gives back the co-derived category rather than a derived category, give us matrix factorizations. So this is sort of somehow some examples on what kind of causal duality we're working with here. And next, I'm going to state the general results due to Positzelski. Are there questions so far? Then I'll continue. Before we continue, I've been a little bit sloppy with this sort of suddenly changing. Yes, people are nodding. Slightly changing between the power series and the polynomial algebra. The way to think of it is if we look at the bar construction of an algebra, I've been completing it, right? Rather than just leaving it as is to get, in my examples, these power series rather than polynomial algebras. And what one should be doing most naturally is to look at the bar construction as co-algebra without dualizing things. And this sort of makes things work out when we're no longer dealing with finite dimensional objects. For example, if I want to look at the exterior algebra on an infinite dimensional vector space, I should really look at the exterior co-algebra. And then the dual of that will be the symmetric algebra on that same infinite dimensional vector space. And so we would like to talk about co-algebras or algebras equivalently, which of course we can't because the dual of a co-algebra is always an algebra, but not vice versa. And this word pseudo-compact that I snuck in earlier is just a cheap trick to get around that. And that is saying the dual of a coalgebra is an algebra, but it has a topology as a limit as finite dimensional quotient. It's a pro-finite dimensional algebra. Because a coalgebra, by the fundamental theorem of coalgebras, is an int finite dimensional coalgebra. It's an inductive limit of its finite dimensional subcoalgebras. And so if I dualize this, I could dualize the whole diagram and look at the algebra, the dual algebra, with its topology as this projective limit of discrete finite dimensional algebras. And then I can take a continuous dual. And if I take a continuous dual of such a pro-finite dimensional algebra, it gives me back a coalgebra. And the word, for some reason, they're called pseudo-compact algebras, but they're really just pro-finite dimensional algebras. And this is, for example, when we're talking about the power series algebra just now, we're talking about the dual of the polynomial coalgebra. And I'm going to talk about coalgebras now to state the results, but one can always go back between algebras, between pseudo-compact algebras and coalgebras by taking continuous dual. And so we'll state theorems for curved coalgebras and their comodules. And this is the dual of a curved pseudo-compact algebra. Right. So for example, often somehow in terms of computing things, it is much more intuitive to work with algebras. Right. So for example, writing down this curvature condition for algebras in terms of the commutator is easier than writing down in terms of the coalgebra, where you have to use the action of the dual of the coalgebra to even define what this commutator means. But here we can say, well, it's just the dual of this, because we just have equations. The equation we can dualize without having to worry about the topology. So you can think of coalgebras as algebras if you keep in mind the topology, but we're going to state theorems for coalgebras because that's sort of the cleaner and there's no op in the way. And then there is this very powerful set of results due to Positzelski about curved causal duality. So we work over a field K, and we have causal duality for arbitrary DG algebras. We don't have to be homogeneous, quadratic, augmented, none of that. And there's an adjunction where the bar construction from a DG algebra goes to a curved conilpotent coalgebra, and then at the left adjoint, the co-bar construction defined in a natural dual way. This adjunction gives equivalent equivalence of model categories. So there's model structures here. Here is the one that you know if you know any model structures on DG algebras, the quasi-isomorphisms are the weak equivalences. Here is a more complicated one, where the weak equivalences are filtered quasi-isomorphisms. But then these two categories are homotopy equivalent. And one can look at modules, and the co-derived category of co-modules over the bar construction is the derived category of A-modules. If I start with a DG algebra, if I start with a curved co-nilpotent co-algebra, I get the co-derived category of co-modules is the same as the derived category of the co-bar construction. So this is sort of a very clean, very general version of associative causal duality. But we want to generalize this even further. And we want to generalize it from algebras. What else could we possibly do beyond algebras? We can go to categories. A category is just an algebra with several objects. And so we would like to replace this term here by the category of DG categories, which also has a model structure. And to do this, there's this very handy trick which I'm trying to advertise. And that is if I wanted to define the bar construction of a DG category, small DG category, to keep things controllable to just a set of objects, we can rewrite what a linear category is. And so this was first described by Aguiar in 97, which we didn't know at the time. So a small linear category consists of a set of objects, and then, well, sets of morphisms between every pair of objects, and so on with the composition. But one way of phrasing that is a monoid in bicomodules over Ks. What's happening there? Well, okay, we have a set of objects, and then Ks takes a coalgebra structure where every element corresponds to this group-like. So like a co-semi-simple coalgebra, the easiest coalgebra I can write down here. It's the direct sum of one for every object. And then bicomodules have a cotensor product, much like bimodules have a tensor product, a cotensor product over Ks. And much like a tensor product is defined as a quotient, a cotensor product is defined as a subobject, as an equalizer of the two actions. And so if I define now a composition is just a partially defined product, if you will, right? It's only defined if S2 here and S2 here agree, if the source and target of my two morphisms agree. And so if I have a cotensor product from VKS to V, so this monoid structure, then because this here is just a sub of V tensor V, and it's exactly that subobject where the source on the right and the target on the left of the morphisms match up. So the way to define a partial multiplication is to define a monoid in bicomodules. And one can further unravel this, and it's indeed exactly the same data to give a small k-linear category or to give a monoid in bicomodules over this coalgebra of objects. So this is kind of cute, and it allows us to just define a bar construction in the way we did before. We sort of take our set of all homomorphisms V, we form some kind of reduction where we remove the units, and then we take the free coalgebra, the free co-nilpotent coalgebra, over a base ring Ks, and we plug in differential and curvature, which are induced by the internal differential and by the composition. And the kind of coalgebra this is, it's a pointed curved coalgebra or a categorical curved coalgebra. So this just means the co-nilpotent coalgebra we had earlier has a single group-like element, and if we quotient it out, the rest is strictly co-nilpotent. And here we have a set of group-like elements, exactly the set of objects. And if we quotient out this set of group-like elements, what we're left over with is strictly co-nilpotent. So that's what's called a pointed coalgebra, or sometimes a categorical coalgebra. Sometimes in co-category, because it really is a co-category, but I'd like to emphasize that it is also a coalgebra. It is an honest coalgebra with particular structure. And with this, we can phrase now categorical causal duality, where we replace, compared to Podolsky's result, the DG algebras by DG categories, And on the left-hand side, instead of curved conal potent coalgebras, we have curved pointed coalgebras. This is an equivalence of equivalent model categories. And then the module categories can also be identified. Derived category of the DG category, which is just sort of looking at all the functors, and the co-derived category of the bar construction. And similarly, if I want to be very precise, I should have some small modification here, but the small modification doesn't actually change the homotopy category. So these homotopy categories are equivalent. And I can talk, instead of talking about DG categories, instead of talking about, this model of, among all the models of linear infinity categories, there's not just DG categories, but there's also these curved pointed coalgebras, which look a bit counterintuitive, right? Why should I think of a coalgebra as being a linear category? And I can recover the objects as these group-like elements. But then the composition is already quite hidden somehow. It's hidden in the differential of my coalgebra. But one thing I'd like to say is that this has very good formal properties. Before I say this, so we're working over a field, but actually, if k is, for example, the integers, this still remains true in principle. I just have to give up on the existence of my model structures. There's no model structures around, but I still have equivalences of homotopy categories. Yes, and so one way of viewing this is to say, this is my Koszul duality for the G categories. This here is a very very fundamental result in comparing different models of infinity categories, of higher categories, where somehow simplicial categories was one of the first models people had, but then they don't have very good formal properties. So then people work with these quasi-categories of Joyal and Lurie. And so this is what can be modeled as simplicial sets with a Joyal model structure. And there's a comparison between these given by the coherent nerve and given by a categorification functor. And these are sort of two models for infinity categories. And this model is the one that has very good formal properties that Lurie writes these long books about, and that a lot of theorems now are proven using this model, because this model is kind of clunky. It doesn't have a good closed monoidal structure, for example. And if I linearize simplicial categories and use dot Kahn, I get DG categories. And if I linearize simplicial sets by just taking the chain coalgebra of a simplicial set, much like if you give me a topological space, I build a singular simplicial set, and I can form the chain coalgebra of that to get the singular chain coalgebra of a topological space. I can do the same linearization here. I have to do some small twist to it, which doesn't matter too much. And then I get a curved pointed coalgebra. So these are sort of a natural linearization of this simplicial model for infinity categories. And this diagram here commutes, homotopy commutes. Meaning that my bar-cobar construction really is sort of a linear version of the coherent nerve. And this is a little bit counterintuitive, because somehow here we're really used to, if we're used to thinking about these objects as, oh, these are just two models of the same thing. Well, there's infinity categories. We know there's a lot of different models for infinity categories, but they're all the same, right? And here we sort of think of this as being two sides of the duality. But really, it's the same. It's just models for linear infinity categories. And one maybe with a special case, if I have just a single object and I just look at infinity zero categories where all my morphisms are invertible, then this commutativity is somehow exactly saying that if I take the loops and then I linearize, or if I linearize and then take the cobar construction, I get the same result. And this is what Adams, when he introduced the cobar construction 56, already showed in the simply connected case. And then in the non-simply connected case, it was only proven quite recently by Rivera and Zanelli, also using kind of higher categorical methods or ideas. And let me say one more thing about additional structures, right? So my claim is somehow that this here corresponding to this here has good formal properties, while this one is sort of intuitive but has bad formal properties. And one way in which DGCAT has bad formal properties, for example, it has a monoidal structure. It has an internal Hom, but the internal Hom and the internal tensor are not homotopy compatible. And so to construct internal Homs of DG categories, one has to do good detours, right? And there's the approach by Koszul in terms of A infinity functors, and there's the approach of Thor in terms of bimodules. But one has to sort of work hard to define an internal Hom of DG categories that is compatible with the homotopy structure. And categorical duality is compatible with additional structures. And so the monoidal structure on here is preserved up to weak equivalence by the bar construction. Right? So this is lax monoidal, and it induces an equivalence of the homotopy categories monoidally. So it's sort of quasi-strong monoidal. It's not strong monoidal, but it's strong monoidal on the homotopy categories. So that's sort of the compatibility. And then I can, on the coalgebras, they have a very natural tensor product. You just tensor together the underlying objects and you sort of write down the obvious things in terms of co-multiplication and in terms of curvature and so on. And there's an internal Hom, which is harder to define. But if I do define these things, I get a monoidal model category. And this is sort of saying exactly that the tensor and the Hom are compatible with each other and are equivalent bifunctors that are compatible with the model structure, which is not the case for the in DGCAT. But DGCAT is enriched as a model category over this monoidal model category. So DGCAT doesn't itself have the good formal properties, but it's a bit like a torsor over curved coalgebras. And so, example, one thing one can do from this is to read off the correct internal Homs of DG categories. And the internal Hom of DG categories, if one finds them by translating to coalgebras, looking at the internal Hom of coalgebras, then they exactly look like A infinity functors. And this was sort of claimed by Koszul a long time ago. And then people didn't actually bother proving it. And then there was one wrong proof in the literature for a while. And then there's been a proof by Canonico, Ornaghi, and Stellari for a few years. But they only prove it over fields. And we prove it over the integers here, as sort of naturally coming out of this this viewpoint of curved coalgebras. So this is sort of the part about curved categorical Koszul duality. And I should pause for questions before moving on to the second part.
I was curious, you mentioned you have to make like a modification of DGCAT. You wrote
Yes.
like DGCAT prime. What would that be?
Yes. So this is so the issue is maybe I should start with the other modification, which is this little star here. This little star here means that I have to take the category of curved coalgebras and I have to finalize it. I have to add a final object by hand. And why is that?
Okay.
Because of the way the curved coalgebras, the morphism of curved coalgebras are defined, there's no actual final object, just because the morphism of curved coalgebras is not just a morphism of underlyings, it also has an extra term. And so there's no natural final object, so you have to add the final object by hand. The final object corresponds to the zero DG category, one object and only the zero morphism. If I have a DG category which has several objects which have just the zero morphism, right? I'm allowed to do that. I can just take a DG category and add another object which has just a zero morphism that's compatible with everything. That does have a natural, because I can't reduce. If I want to reduce, I have to kick out the unit. I can't go up by the unit, so I can't reduce, so I can't define the bar construction. And there's two ways of solving that. Either I could add extra coalgebras by hand for each of these DG categories with an element, with an object with a zero morphism only, or I just kick out all of those objects. I say I only allow an object with only zero morphism if that's the only object in the DG category. And because I can always replace any arbitrary DG category. If I have just zero morphism, I just add an identity and a homotopy from the identity to zero, and that's going to be homotopy equivalent. So it doesn't change my homotopy category if I do this. So this DGCAT prime is equivalent to DGCAT. It's equivalent model category.
I see. Thanks.
Yeah, so it's really a very, very minor modification. Right, and I mean also if I want to do this over a PID, I should also restrict myself to quasi-free DG categories. So that taking the tensor products in the bar construction doesn't run into any trouble. But again, I can replace any DG category by a quasi-free DG category where all the Hom complexes have underlying free graded objects.
Yeah.
Okay, any other questions? Then let's talk about more extra structure. And I'm going to start by revisiting a topological example, which is this causal duality between singular chains on topological space and the chains on the loop space, the base loop space. And if I want this to be a DG algebra rather than infinity algebra, I take the Moore loop space, but that's just a technical thing. And as we've just said, the cobar construction omega is the linearization of the base loop space, right? And this is expressing that there's a causal duality between those two categories. Right, we can make it precise by picking a point, right? So there's somehow this has a special point in the G algebra. This a priori has many points, but we can replace it by a model with only one point. And then if we look at modules for this, I get that the co-derived category of the chain coalgebra by causal duality is the derived category of the cobar construction, which in this case is the same as the derived category of chain on the loop space. And now this derived category of chain on the loop space is exactly this category of infinity local systems on X. It's exactly those complexes of sheaves on X whose cohomology sheaves are local systems. And so this is what I promised earlier, that this co-derived category would capture this extra information. And here indeed it captures the whole representation theory of chains in the loop space. So it knows a lot about the fundamental group, right? And you're sort of used to thinking that the chain coalgebra loses a lot of information about the fundamental group, but it only does if you look at it up to quasi-isomorphism. Now we are going to introduce Calabi structures. So this is an interesting structure that an algebra or category can have. And it's a shifted self-duality. So if I start with A, let it be DG algebra, it could be DG category, but algebras are enough to think about for now. And then I say the dual should be equivalent to some shift of the original A, and this equivalence should be as A bimodules. So quite a lot of structure, and it should also be S1 equivariant in a sense that I'm gonna make precise. And so these Calabi structures, so Kontsevich thought about these. Costello introduced them in studying open-closed field theories. And they're very present at the moment. They sort of occur in many different situations. You sort of can prove that many interesting algebras are Calabi algebra, have Calabi structures. Of course, the name comes from the fact that if I have a Calabi variety, then the derived category will have a Calabi structure. And they come in two flavors. So I said dual here. I didn't specify what kind of dual. And because we're talking about bimodules, we could talk about a bimodule dual. So A shriek is just the bimodule Hom from A to AE standing for the A tensor A op. Or I could take a linear dual just over K from A to K. And these are two different duals. And so there's two different flavors of this Calabi structure. I could either say, okay, A shriek should be equivalent to A shifted by N. And this is a so-called smooth Calabi structure. Or I could say, I could have a proper Calabi structure where A is equivalent to the other A dual, right? So a linear dual equivalent to A with some shift. And I think I have a minus N here. There's a little bit of a question of the grading convention. I'm going to use homological grading just because that's what our examples naturally have. And then it's called smooth and proper because, so A is smooth if it's as a bimodule over itself, it is compact. And so if sort of this looking at A over AE is sort of a nice compact object. And so taking the shriek is this dual is sort of a natural, nice thing to do. And if A is compact as a K module, we say it's proper. And then this dual is sort of the natural, nice thing to do. And of course, many interesting examples are both smooth and proper. For example, the DG category of a algebraic smooth proper variety will be the smooth proper DG category. So again, this notion of smoothness, homological smoothness, corresponds exactly to smoothness of algebras, to smoothness of algebraic varieties, and this corresponds to properness of algebraic varieties. That's where these words come from. Um, right, and so there's two kinds of Calabi structures. Let me give you some examples of what, where these occur, and I'm going to keep my running topological example. So the cochain algebra of X has a proper Calabi structure if X is a closed-oriented manifold. And this is just Poincaré duality, right? So I take the cochains of X, I dualize this to get the chains of X, and I introduce a shift, and then I have a quasi-isomorphism between those two things, and that's exactly giving me Poincaré duality. And because X is closed on its manifold, I can find some small enough model for cochains so that I indeed have a proper DG algebra with a proper Calabi structure. There's also a smooth Calabi structure associated with a closed-oriented manifold if I take a chains on loop space. So chains on loop space as a DG algebra actually has smooth Calabi structure. And I've skipped the numbers. So this is an n Calabi structure. This is an n Calabi structure where the dimension of X is n. And this is a much harder theorem than Poincaré duality. But it's also true. It's proven by Kohlgatra in a draft paper and then by Braff Dickerhoff. And let's look at these two examples, right? So if we go to the proofs for this example 2, for the smooth Calabi structure here, they use Poincaré duality. And they use Poincaré duality, but not just Poincaré duality, they use Poincaré duality with coefficient, so stronger notion. But the fact that somehow Poincaré duality has something to do with both of these, and the fact that if I have this, I get a proper Calabi, and if I look at the co-bar construction, I get a smooth Calabi, suggests that smooth and proper Calabi structures and Koszul duality are related, and are maybe related by being swapped around. And indeed, that's what Kohlgatra already observed in some class of examples, that Koszul duality switches around the Calabi structures. But they look at Koszul dual algebras, so that's sort of quite restricted. And in particular, from the topological point of view, they only look at simply connected spaces. And if X is not simply connected, then one issue, of course, is that the cochains on X up to quasi-isomorphism is a weaker invariant than the chains on the loop space. Right? Chains on the loop space knows about the fundamental group. Cochains up to quasi-isomorphism doesn't know as much about the fundamental group. And Poincaré duality is strictly weaker than the Calabi structure for chains on loop space. So there's not manifolds, but other topological spaces that satisfy Poincaré duality for their cochains, but they don't have the smooth Calabi structure here. And if you look at this, you should be in a way unsurprised, because maybe Poincaré duality, so if you're a topologist and you look at this, you would say, oh, well, Poincaré duality for simply connected space is not somehow the correct condition. You should look at Poincaré duality with all systems of coefficients. And if you've listened to the talk so far, then you should also be suspicious about looking at C star X up to quasi-isomorphism, because this sort of lives naturally on my Koszul dual side, where I've been using the stricter notions of weak equivalence. And so to put these together, we look at let's take a chain instead of the cochain algebra, right? The chain coalgebra. And we look at it as a curved coalgebra. Happens to have zero curvature, but we look at it as a curved coalgebra. And we look at it up to weak equivalence of curved coalgebras, which is a different notion than quasi-isomorphism. And it's going to be proper if X is a finite CW complex. I haven't actually defined what a proper coalgebra is, but in particular, if I have a finite dimensional coalgebra, it's going to be proper. Or if I have a coalgebra weakly equivalent to a finite dimensional coalgebra, it's going to be proper, much like a proper DG algebra. It's a little bit more subtle for coalgebras. So there's also some non-finite dimensional coalgebras that are also proper. And then a proper Calabi structure on a pointed curved coalgebra is going to be a suitable weak equivalence to its linear dual. And now this is going to be weak equivalence. So it's going to be a notion stronger than quasi-isomorphism. It's going to be weak equivalence as as CE comodules, right? As bi-comodules over C, much like before we were looking at weak equivalences as A bimodules. Now we're looking at C bi-comodules. And this weak equivalence, which means something like there's going to be a co-acyclic cone rather than it being a quasi-isomorphism. And so we can define proper Calabi-Yau structures on coalgebras. Of course, this is quite an abstract definition now because we have this this new notion of weak equivalence, which is defined in this abstract way. But one key observation is that if C is sufficiently co-commutative, so chain coalgebras are not strictly co-commutative, they're E infinity, then this notion of weak equivalence can actually be tested by testing with coefficients. So this is equivalent to Poincaré duality with coefficients. And so this is how Poincaré duality with coefficients, which is a stronger notion than just a quasi-isomorphism between chains and cochains, is actually strong enough to get a proper Calabi-Yau structure on the coalgebra. And then what we show is that a proper Calabi-Yau structure is exactly the same as a smooth Calabi-Yau structure on the dual. So this is now the theorem I want to state. I have one slide about the S1 equivariance, which is just as a brief aside, maybe, right? So we're interested in maps from A shriek to A, with a possibility with a shift here. And this happens to be the same as Hochschild homology of A. This is just a computation. And then Hochschild homology, there is a map from negative cyclic homology to Hochschild homology. And this is somehow some kind of S1 invariant in a derived sense subspace. And so if I have my Calabi-Yau structure, a priori it's going to be some weak equivalence, some map in here. So I can look at its image in Hochschild homology. And then the question is, does it come from some element in negative cyclic homology? And this is somehow this S1 equivariance. And if I only have a map element here inducing my equivalence, it's called a weak Calabi-Yau structure. If it comes from negative cyclic homology, it is an actual Calabi-Yau structure. And dually, one can do the same thing for the proper structures where we have the other dual, and this is sort of from dual cyclic chains, again, a lift giving this S1 equivariance. So this is just sort of an aside if you're interested in what I mean by S1 equivariance. But let me turn back to the main theorem. So this is now with Manuel Rivera. If you look at DG category A over the integers, and it's smooth if and only if the bar construction is proper. And then a smooth Calabi-Yau structure on A corresponds exactly to proper Calabi-Yau structure on BA. All right, and so in particular, the proper Calabi-Yau structure on chains on X, which comes from Poincaré duality with coefficients, allows me to recover the smooth and Calabi-Yau structure on chains on the loop space. And I have time to say a little bit about the proof. In the proof, I have to compare, right, this maps of AE modules between A shriek and A shifted. And on the other hand, the proper Calabi-Yau structure on the coalgebra should be the linear dual, should be compared to the shift of C as CE comodules. But I know that the derived category of AE and the co-derived category of CE are equivalent by Koszul duality. So the only thing we have to check is that C corresponds to A and C star corresponds to A shriek. Under Koszul duality, and I'm just going to not actually compute it for you, but say why it's unsurprising this is true. It is really just a computation. But if you recall that the basic property of Koszul duality was that somehow the free rank 1 object here goes to the trivial here, and the trivial here goes to the free rank 1 thing here. And then the comodules A and C are exactly somehow the Goldilocks position, right? So A is between K and AE here, and C is between K and CE here, and they exactly are matched with each other. And similarly for the duals. And this gives the main result if we have set up everything correctly. And yeah, I have one more example. Yeah, so I've been going a bit too fast. So if you have questions or want me to stop or repeat something, feel free to do that before I turn to the last example. Right, then let me give the last example. First of all, I should mention that there's similar results have also been obtained by Matt Booth, Joe Chang, and Andrey Lazarev recently. So we sort of realized last summer in Wolf that we were working on the same thing. But actually, so somehow the papers do have a very significant overlap in the things we care about, but they also do lots of interesting things that we don't consider. And we do some things that they don't consider. So I think that they nicely complement each other in the end. And yeah, so this is an algebra seminar. So I normally, talk about topology seminars often. And my examples have been quite topological. So let me give you an algebra example to maybe make you a little bit happy. Another application connects to different results about Lie algebras. And so this is sort of this class of unimodular Lie algebras. So I take a finite dimensional Lie algebra, and I take the top exterior power of the adjoint rep. And if that is trivial, I say the Lie algebra is unimodular. And this is quite a nice notion. And it's really very general. It covers both semi-simple and nilpotent Lie algebras. And Hasewinckel in 1970 proved that if I have a unimodular Lie algebra, then I have Poincaré duality. I have the homology and the cohomology of a Lie algebra are identified with a shift for arbitrary modules as coefficients. So he proved something more general. He essentially proved this where I twist this with this top power of the adjoint, and of course, if that's trivial, I can remove the twist. Much like Poincaré duality exists in a twisted version that is more general if my manifold is not oriented. So it's entirely analogous. And this is also equivalent to saying that the coalgebra of Chevalier-Eilenberg chains has a proper N-Calabi structure. And this should be unsurprising from what I've told you. I've told you that if I have a co-commutative coalgebra, then I can check this weak equivalence with the dual, that this is really weak equivalence, not just a quasi-isomorphism, by checking with coefficients. And checking with coefficients exactly gives me this computation of Lie algebra homology and Lie algebra cohomology. And another interesting property of unimodular Lie algebras is that the universal enveloping algebra has a smooth Calabi structure. And so this is by He, Van Oostijn, and Zhang from 2010. They showed weak smooth Calabi structure, so they don't have the S1 equivariance. But we get the S1 equivariance almost for free because the S1 equivariance here is very easy. It really sort of a one-line computation of saying, oh, the cycle that induces this equivalence, which is explicitly written down in the literature, if I apply my my cyclic differential, my con B, then it vanishes. And so I get the invariance. And so I get that this has an actual smooth Calabi structure, not just a weak one. And yeah, this is what I wanted to say. So thank you for your attention.
Yeah, thank you very much. A nice talk. Are there any questions? Yes.
I had a question. Thank you very much for the very nice talk. If I may come back to the topological examples, which I find also very interesting. For example, I mean, there's a lot of discussion about singularity categories for BG, for the classifying space of finite groups, or also about formality of C star BG for compact Lie groups. Does your machinery give some insight into these structures and maybe get some more refined output?
That's an excellent question. I don't know because I don't know about these questions. So you're saying
there's some papers by Benson, Greenlees, and some others, I think, which study these singularity categories for BG, for example, for finite groups.
Right. Yes. So yes. So this. So this. I know. Yes. And they, like, for example, they prove like these, look at the spectrum of those categories.
Right.
This thing.
Yeah.
Yes, I haven't actually, not sure about the Calabi thing, but one, like, some of this stuff is sort of, it can be quite naturally seen as Koszul duality results, right? Where sort of you have your, right, because these categories are sort of stratified by the group cohomology,
Right.
and this is essentially the bar construction of the group ring. Yes, and so and then there's sort of so you can say this co-derived category, right? This stable category as sort of being a singularity category being a portion of the co-derived category, and then the co-derived category is the derived category, essentially representations of the bar construction. And then there's sort of some results how to stratify those by Greg Stevenson, I think. And then one can translate that. And there's some issues about the involved algebras not necessarily being nilpotent, but I think there's some yeah. So a student of mine is actually looking at related things at the moment. And the other question, formality of
Well, I think for C star BG,
yeah, right, because that's sort of
or Lie group or compactly group, let's say.
yes, yeah, that's sort of then becomes interesting to know if this is formal, because if it's formal, then the derived category is much nicer to analyze. But this may well be like a separate difficult question to answer in order to apply the machinery rather than a question that this machinery helps answer. But I'm not sure. Yeah.
Thank you.
Yeah, another question.
Manuel?
Hi, how are you, Julian?
I'm good, thank you.
Yeah, nice talk. Thank you. So I was wondering, I don't know if I've asked you this question before, but is there any possibility that there's a general abstract Koszul duality statement that encompasses all of the versions of Koszul duality we know, and also maybe the classifying space loops equivalence or adjunction as particular examples?
Right. So you're saying that sort of that has both the linear and the
Yeah.
non-linear version as special cases. Yeah.
Yeah, like or do you know what's the most general Koszul duality statement that one can make?
Yeah, I'm not sure. Right. I mean, so in a way, that's sort of that, like the Matt and Andre's version of global causal reality is sort of in the linear side quite quite general. And one can recover the other ones to some extent from it. But I think like having some statement that would have both the linear and the nonlinear version as sort of special cases would be very interesting, but I really don't know how that would look.
Okay.
Yeah,
Thank you.
Arguably this is all just associative causal reality, and of course one should look at the operatic level, but then
Right.
the operatic level people aren't so far very happy with curvature as far as I can tell. So
right.
Yeah.
But they also sort of have a very similar form and even similar proof, right?
Yeah. No, I think there probably is a proper curved operatic version out there, which I don't think has been formulated yet. Although there's some people doing stuff in that direction. But yeah, but a linear nonlinear version, that would be very interesting, but I have no idea.
Yeah. Okay. Thank you.